Hello once again, class, and welcome to another mock lecture. In this video, we are going to be talking about limits involving infinity, which breaks up into really two categories. There's limits at infinity, and then there's infinite limits. I talked a little bit in class about infinite limits, but I just wanted to do a quick recap for the video folks, just so that they're caught up to speed. So first, let's talk about infinite limits. What I've drawn here is the function f, and in class, what we decided for the behavior as x is approaching a from the left and from the right, we said is equal to negative infinity, which out the gate doesn't make any sense, right? Limits are supposed to converge onto some kind of number. They're supposed to be equal to L, where L is some real number. Negative infinity is not a number. Negative infinity is a concept. The reason that we write this instead of does not exist, right? Because, I mean, let me be clear. The limit as x approaches a does not exist. We're not writing that, though, because we're writing this instead to inform the reader that, hey, there's a special behavior going on with this graph at a, namely, as you approach from the left and from the right, your graph is approaching negative infinity. Our graph is going to get however large we want it to be in a negative direction. So maybe I should say however small we want it to be as we take x values that are sufficiently close to a on either side of a in this particular case. Since the left and the right hand limits agree, we could just say this. Now let's say that our graph did this instead. Okay, now here the left hand side is still approaching negative infinity, but the right hand side, as you approach a from the right, now we're going towards positive infinity. So notice that now I changed my limit as x approaches a of f of x. Now I'm saying that it doesn't exist. But to be clear, and let me go back a couple slides, it doesn't even exist here. But I'm not writing that because the left and the right hand limits agree that it does not exist in this very specific way where it's going towards negative infinity. Here, though, I do have to say that it does not exist because the left and the right hand sides don't agree. And if you wanted to get that special behavior, right, if you wanted to figure out that there's the existence of a vertical asymptote, you'd have to find the one-sided limits. You can also have one side of the graph just not even exist, right? In this case, the only statement we can make is this one. The limit as x approaches a from the left of f of x is equal to negative infinity. We can't even, this doesn't even exist because there's no right-hand limit. Now, all these situations are the definition of what a vertical asymptote actually is. Now that we know what limits are, we can actually define a vertical asymptote. A vertical asymptote is a line x is equal to a where one of these is happening. That's it. That's what a vertical asymptote is. So if you find that the limit as x approaches a from the right is equal to positive infinity, like this one, automatically you know, okay, well, there's a vertical asymptote there. And as I approach this vertical asymptote value, a, from the right, my graph is behaving in this very specific way. Okay? So let's do some examples with this stuff. All right, example number 1. Evaluate the limit as x approaches 0 of the natural log of the tangent squared x function. So we're throwing a tangent squared x function into a natural log, and you might be tempted to just say this based off of a limit law, but there's a problem with this. That limit law, which I think we talked about in the continuity section, I think it was continuity of composite functions, stipulates that whatever this is, this limit, the limit as x approaches that whatever specific value that we find here, has to actually exist. But the limit, and I should really write the limit, as x approaches 0 of the tangent squared of x is just 0. I guess if I'm going to change the notation, I should change this as well. Is equal to 0. Okay, that's just by direct substitution. Well, this thing right here is not continuous at 0, so we actually can't use that limit law. We can't talk about that continuity theorem for composition functions. So instead, we have to work around this in a kind of actually a pretty cool way. We're going to do some kind of substitution here. But the main question is, what is this function doing as x approaches 0? That's what I need to figure out. So I drew the unit circle, and I did say let's let tangent squared of x is equal to k here for a second, but let's ignore that for 1 second. I just want us to focus here. What I did is I drew quadrant 1 and quadrant 4 of the unit circle. And the reason I did that is because we're approaching 0, and I want to look at what's happening as you approach 0 from the left and as you approach 0 from the right. And as you may remember, the tangent function takes radian measurements as its input or degree measurements as its input. And so what I'm doing is I'm plugging in stuff that, is in quadrant 4. So we're looking at what's going on at negative pi over 2, and we're increasingly getting that smaller until we're 0. And then we're looking at pi over 2, and we're decreasing that, right, until we get to 0. So this direction is from the left. This direction is from the right. Well, let's take a look at what's happening to the tangent squared x as we approach 0 from the left and from the right. Well, the first thing we know is that, and I already wrote this, we know that our limit is actually 0, right? It's a continuous function. That's x. It's a continuous function, so we're just using direct substitution to get that that's 0. But look at the y values as we approach 0 in both quadrants, right? When you're plugging in negative stuff, because we're squaring this function, and remember, tangent's defined to be sine over cosine. So in this quadrant, tangent is normally negative. In this quadrant, tangent is positive. But because we're squaring it, our solutions, right, our outputs for the tangent function are always going to be positive. So as you approach 0 from either direction, the output, tangent squared x, is a positive number that's getting smaller and smaller and smaller and approaching 0. So now, when I'm saying that we're letting the tangent squared of x be equal to k, what we just figured out is that no matter what k is, it's going to be greater than or equal to 0. It cannot be negative because we're squaring it. It's really by nature of squaring. And so what that means is as x gets closer to 0, k is also getting closer to 0, but only from the right, only from positive numbers. And that is very important, because there does exist a right-hand limit for the natural log function. Oh, and by the way, here's my important substitution. So what I'm doing is I'm saying this thing is now equal to the limit as k approaches 0 from the right of the natural log of k. Okay, it's just this thing down here. Because we know k is approaching 0 from the right, as x approaches 0, I'm utilizing this substitution. Right, I'm replacing this with k. And now I need to look at what k is doing. I don't care about x anymore. I care about k. All right. Well, the natural log function looks like this. Right? This is the natural log function. If you plug 1 into the natural log function, you get 0. This is 1 right here. Maybe 1 on the y-axis is somewhere here. So like here's e. But anyway, the domain of a natural log function is only 0 to infinity. You can only plug in things that are bigger than 0 to a natural log function, which is good, because if we're looking at the limit as k approaches 0 only from the right, as x gets closer to 0 this way, well, then it looks like k, right, the natural log of k is approaching negative infinity. Right? It's just going to go down forever and ever and ever. So it's just equal to negative infinity. So by transitivity, then I can say, okay, well, then the limit as x approaches 0 of the natural log of this tangent squared function is equal to negative infinity. But again, to be clear, the limit as x approaches 0 for this natural log function, it does not exist, but we're informing the reader that there exists this really cool thing. And actually, if you graph this, and I invite you to, you'll find that both the left and the right-hand sides are approaching negative infinity. All right, example number 2. Let's evaluate the limit as x approaches 0 of 1 over 1 minus cosine x. Again, we can't plug in 0 here, because that would give us 1 minus 1 in the denominator, right? So we can't use a direct substitution in this particular case because it's not continuous, it's 0. 0 is not in the domain of this function. So we have to do this kind of substitution idea again. So I'm going to let k be equal to 1 minus cosine of x. So I'm going to rewrite this now only in terms of k. Right? So the limit as x approaches 0 of 1 over 1 minus cosine x is the same as the limit of 1 over k as k approaches, well, we don't know yet, right? We have to kind of figure that out. So we have to ask the question, well, what is k doing as x approaches 0? So to figure that out, I'm going to realize that 1 minus cosine x is greater than or equal to 0 always, right? Cosine x oscillates between negative 1 and 1. If you put its minimum value in there, you'd have 1 plus 1, which is 2. That's definitely positive. And if you plug its maximum value in, which is 1, you'd have 1 minus 1, which is equal to 0. So this thing is oscillating between negative 1 and 1, but it's only producing positive values. The other thing to keep in mind is that we can evaluate what this limit is at 0. Cosine function is continuous at 0 by itself, and it's not in a denominator. So the limit as x approaches 0 of 1 minus cosine x is the same as 1 minus the cosine is 0, which is 1 minus 1, which is 0. That's just by direct substitution. So we know two things. We know that k, right, 1 minus cosine of x, always positive, and we know that its limit as it approaches 0 is 0. So again, we get this one-sided limit, just like in the last one. K is approaching 0 only from the right as x approaches 0 itself. So I'm going to replace this question mark here with 0 from the right. Now I want to take a break here, and I want to talk about just the 1 over x function in general. Knowing the shape of this graph is super important and actually helps us do a lot of things, even in this one video. Right? The first application will be here. The next application will be when we start talking about limits at infinity. But this particular graph, notice that as you're approaching 0, the left-hand side is approaching negative infinity and the right-hand side is approaching positive infinity, which kind of makes sense, right? If you start plugging in some particular values into this function, like, 1 over, I'm just approaching 0, right? So 1 over 1, right? That's 1. Then you could do the next one, which would be like 1 over 0.1, right? Which is 10. Then you could do 1 over 0.01, which is 100, 1 over 0.001, which is 1,000. So as we're getting x to be closer and closer to 0, we're getting bigger and bigger numbers for y, and that's why this is happening on the right. I could replace all these in the negative sign, so you could see, oh, that's why this happens. Right? That's why this behavior happens. So it's important to know these two things that I circled, right? These one-sided limits as x approaches 0 for 1 over x. In this particular case, we're approaching from the right, so that was just infinity, right? That was this side only. That's a terrible graph, but hopefully you get the idea. Okay, so that means that this is equal to this. So now let's switch gears and talk about limits at either plus or minus infinity. And the way that I think about the limit as x approaches infinity, right? And that's kind of the new piece here. We're not approaching a number anymore. We're looking at what happens to the function when x gets really big, right? What happens when it gets really small? This is like end behavior for polynomial functions back in pre-calculus. Of course, now we're applying this idea of quote-unquote end behavior to all functions, but that's basically what this means, right? When you're looking at x approaching infinity or x approaching negative infinity, what you're talking about is a right end behavior and a left end behavior. Overall, what does the function do on the left? And what does the function do on the right as the absolute value of x gets really, really big, right? Arbitrarily large is the way that I stated it here. To illustrate my point, let's consider this graph r of x here, which is 2x squared plus 7 divided by x squared plus 2, and it looks like this. Okay, it actually has no vertical asymptotes because nothing makes the denominator 0, at least no real number does. So, okay, you can plug in whatever you want to this function, but it does have a horizontal asymptote. It happens to be at 2. Overall, what happens is that this graph approaches 2 as x gets really, really small, right? Approaches negative infinity, and also as x gets really, really big. The reason why is because when you're looking as x approaches infinity or as x approaches negative infinity, these constants that I've circled, right, the plus 7 and the plus 2, start to become really meaningless. Like, okay, if x is 10, then okay, 7 and 2 even is relatively sizable. But when x is a billion, adding 7 to 2 times a billion squared is not really adding that much overall, right? Same with adding 2, right? A billion squared plus 2 might as well just be a billion squared. Like, how much the 7 and the 2 are affecting the graph start to become really negligible as x gets really, really big, and that's kind of one explanation for why that's happening. So in general, we can say that the limit as x approaches infinity of f of x is equal to L means that values of f of x can be made as close to L, in our last example it was 2, as we like, by taking x to be sufficiently large or sufficiently small, right? We can make the same argument for the limit as x approaching negative infinity of f of x, right? Also being equal to L. If either of those two limits are true, that the limit as x approaches infinity of f of x is equal to L, or the limit as x approaches negative infinity of f of x is equal to L, then y is equal to L is called a horizontal asymptote. most rational functions have a horizontal asymptote, right? Typically just one. But you can have functions that have more than one, right? Think about the arctangent function, right? Which is actually bounded by y is equal to pi over 2 and y is equal to negative pi over 2, right? That thing actually has two horizontal asymptotes. Because you can make this statement for pi over 2 on the right, and you can make this statement for negative pi over 2 as x approaches negative infinity, right? So that one actually has two. Before we get to some examples, let's return to f of x is equal to 1 over x. Particularly, if you're looking at what's going on with this function as you get bigger and bigger, as x gets bigger and bigger, it appears to be going to 0, right? If we start plugging in bigger and bigger numbers for the denominator, this is 0.01, right? This is 0.001. This is a googol. 1 divided by a googol. It's point and then 100 zeros and then 1, right, is what that would look like there. Actually, I think it's 99 zeros and then 1. So it's getting really small. It's approaching 0. Same thing on the left, right? We could do the exact same thing where you just have 1 over significantly smaller and smaller and smaller numbers. 1 over negative a googol is negative 0.9 and then 99 zeros with a 1 after that, right? We're getting closer to 0 as x gets really big, and also getting closer to 0 as x gets really small. These limit laws, right, that we've learned also work at infinity. So one thing that we could do with the information that we know, I guess there's two pieces. There's the limit laws, and then there's also the fact that we know the limit as x approaches really plus or negative infinity of 1 over x is equal to 0. And this is terrible notation, and you should never do that. I'm just trying to abbreviate myself here. But I'm using positive infinity in this example. What we can do is if we wanted to figure out what happens when you raise that to the nth power, you can rewrite it using a limit law like this, right? That's the power law for limits. We could similarly, we already know, right, that this thing is equal to 0, but we can similarly apply the power to both numerator and denominator. So we're getting the limit as x approaches infinity of 1 over x to the n, right? But this is 0. So by transitivity, this thing is 0. And we could say the same thing about x approaching negative infinity, by the way. That's really important moving forward, and I'll show you why with another example. All right, so in this one it says evaluate the limit as x approaches infinity of 2x squared minus x plus 11 divided by 7x squared plus 15x minus 1. All right, what I'm going to do is I'm going to divide every single thing, every single term that exists in the numerator and the denominator by x squared, just because I can. Right, that's just something I can do. Then I'm going to start applying some limit laws to this. So I'm going to apply the quotient law, bring in the limit as x approaches infinity to the numerator and denominator, then some sum and difference laws. And in this step, I also simplified. So for example, 2x squared divided by x squared, that's just 2. 15x divided by x squared, that's 15 over x. So I got this thing. Then I just started evaluating stuff, right? Using the theorem that we just kind of learned, this approaches 0. So do all these. These all go to 0. Even if there's a constant out front, like 15 over x, that should be a 15 there. Bring the 15 out in front using the constant law. Then you've got 15 times the limit as x approaches infinity, that's infinity, of 1 over x. That's 5 times 0, right? That's 0. So 15 times 0 is still just going to be 0 there. Same thing with 11. So this just simplified into 2/7. This is a constant law that I'm using here. The limit is x approaches infinity of 2. X is not influencing that at all. So we just get 2/7. And that's corroborated with the fact that if you look at this thing in a pre-calc setting, the degrees of the numerator are the same. So you just take the leading coefficients and you divide them by each other to get the horizontal asymptote, which, as we know, is what y is approaching as x gets really big or really small for a rational function. You can even do it for stuff like this. Evaluate the limit as x approaches infinity of 3x plus 4 divided by the square root of 4x squared plus 1. I'm going to divide everything by x. Now, dividing by x in the denominator can be written in a fancy way, right? I can write it as the square root of x squared so that I can actually divide stuff on the inside, since you can divide radicals like that. Right? If you have the square root of a divided by the square root of b, that's the same thing as the square root of a divided by b. Right? That's what's going to happen here. But fundamentally, I'm not changing the integrity of this fraction because I'm dividing by the same thing. square root of x squared is just x. So I get this. I simplified here. I got 4 over x here. That's going to simplify. And then I'm just going to bring this limit in using some limit law stuff. So I'm going to get the limit as x approaches infinity of just 3 plus 4 over x divided by the square root of 4 plus 1 over x. Using limit laws gets me this stuff. This goes to 0. This goes to 0. That's just 4, and that's just 3. So we just get 3 over the square root of 4, which is 3/2, and we're done. Horizontal asymptote, x will be approaching 3/2 as x gets bigger. Now there's one other function that I want to look at before I end the video for today, and that's an exponential function, right? Y is equal to e to the x is important to know. This thing has some special I was going to say one-sided limits, but limits at infinity. Negative infinity and positive infinity behave differently in this example, in this graph. As we approach negative infinity, there's a horizontal asymptote, right, for this exponential function. The limit as x approaches negative infinity of e to the x is equal to 0. But if you approach positive infinity, you can have a limit at infinity that goes to infinity, right? That happens all the time, actually. With polynomials, that's what happens. But as you approach, as x gets bigger and bigger, for e to the x, the y values also get bigger and bigger. So we can say stuff that looks like this. Again, technically here you'd say the limit does not exist, but this is showing the reader that, hey, a special behavior is happening. It's going up forever and ever. So let's evaluate the limit as x approaches negative infinity of the sine of e to the x. Well, just using this fact, we can make a substitution. Right? The limit as x approaches negative infinity of sine of e to the x, let's replace e to the x with a k, is the same as the limit as k approaches something for the sine of k. We already know it's 0, and it's always approaching it from the right, right? Because these numbers are always positive. They're always above the x-axis here. So this is just a one-sided limit for k approaching 0 from the right of sine of k, and we can just take care of that. And we can just take care of that with direct substitution, right? It's just the limit. No, it's not even that. It's just the sine of 0, right? Which is 0. Which means that the limit as x approaches negative infinity of sine of e to the x is equal to 0. All right, and that's it for this one. Just wanted to do a few examples for limits at infinity, recap some infinite limit stuff as well. Hopefully you guys learned something. Thanks a ton for watching, and I'll see you in the next one.